Yeah, what we reported on yesterday was really getting our first solid sample into SAM and ChemIn. And the ChemIn is a instrument that measures mineralogy with X-ray diffraction. And they had reported on the results a few weeks ago. And so this was really the first time we had a chance to report to the public on our results. I read on the blogosphere this morning, the cameras put out their images right away. Why don't you guys put out your stuff right away? And it's not like we're trying to hold things back, but what we really get is an incredibly complex set of spectra. The tunable laser spectrometer is something where light bounces back and forth, and you use the strength of the lines to determine isotopes. And even though if you go to the world's best databases, they still don't have those lines perfectly calibrated. So our team really has to go back and do spectroscopy and look at those lines and try and get it right. And if we sent that data out, of course, we get misinterpreted and so on. So we try and process it a little bit before we really get the news out. Same thing on the gas chromatograph and spectrometer data. We build up kind of our own internal libraries, and we know what contaminants might or might not be in our system. And if that result was to get out very, very rapidly, it would be misinterpreted again, and there'd be all sorts of speculation. So we're just trying to do things in an orderly way and not hold back things from the public, but get them out as soon as possible. So I'd really be glad to answer any questions anybody might have about SAM or the mission. Right now did anybody from the mission talk to you? So right now we scooped this sample, which was intended to clean out the sample processing chain. And now we're really very carefully looking for the first site to drill. There are all these beautiful layers, and the question the team's looking at, are these sedimentary layers formed by aqueous water deposition, or are they lava flows formed by impacts or formed by volcanoes? And so by getting better pictures and microscopic imagers and maybe elemental analysis with the arm, we're trying to decide what really are the best rocks to drill into. But hopefully before the end of the year, we'll drill into a rock, get some sample, and again analyze it with SAM and ChemIn. But I'd be glad to answer any questions anybody has about the mission or what we're doing next, what the long-term goals are.
How closely are SAM and ChemIn working together? Do you guys pick the same stuff and share results, and as a result of that, you get things you can release to the public?
Yeah, absolutely. What we were kind of really looking for in this sample is, are there any minerals that ChemIn sees that we also see? For example, if there's a carbonate from an aqueous stream or a little lake or something, and they detected it with ChemIn, and then we also saw CO2 release as we heated it up and the carbonate broke up, then that would be fabulous, because then we have a reference point against each other. It turns out that none of the things that they saw this time we can uniquely identify, and that's because there's this amorphous stuff that they don't see, number one. And number two, some of the minerals, the gases that we saw from minerals, were just so low abundance that they wouldn't have seen them anyway. But we try and do everything we can to coordinate. And if you're going to drill, it just takes days and weeks to get ready. And so we may as well do both analyses at the same time.
Any surprises so far?
Yeah, I think, yesterday we tried to report on most of them. We saw those chlorocarbons, methyl dichloro and trichloroethane, methane, and we saw a lot of water. That was surprising, several percent. We secured a deuterium to hydrogen ratio in the water, which is really a big deal, because those are things that track how the atmosphere might have been lost over time, over billions of years. One of the biggest surprises that the people who worked on the Mars exploration rover, Spirit and Opportunity, told me they were surprised, and I didn't work on that mission, so I couldn't be surprised, was the evolved SO2, sulfur dioxide, which kind of points toward sulfates even in this wind-blown dust. So that was very surprising to them.
Does that mean more volcanism or something?
Yes, certainly. The sulfur could have come from volcanism. The chlorine that we see in our perhaps calcium perchlorate is what we think it is. Could have come from atmospheric processes, but just formed from volcanism. The thought is that volcanoes have happened not necessarily real recently, because we've not seen them from orbit. There are no hot spots that we can detect, but there are some very smooth plains and surfaces. And what happens is, once you form a smooth plane by, let's say, a volcanic outflow, then the cratering starts to happen, because Mars has a very thin atmosphere, and what might burn up in the Earth's atmosphere eventually just craters. So some of these volcanic outflows are judged to be perhaps tens of millions of years old, which is really, really young on a Mars scale. Yeah.
How likely or unlikely do you think it is that those compounds are not indigenous compounds?
How likely or not likely those compounds are indigenous? My personal guess is that almost certainly the chlorine is from Mars, because we didn't take any with us. And then we have just a little bit of our vapor of our chemical derivatization agent. It's a fairly complicated molecule. It's possible that that is the carbon that's there. I don't really think so, because when the perchlorate was breaking up, that's exactly when those chlorinated species came out. So I think what happened is it's some sort of carbon that's in the sample there that is Martian. So I think both the chlorine and the carbon probably came from Mars. But what form that carbon in, even if it is Martian, is really hard to tell, because all you see are these real simple breakup products, chemical products. And so if there's enough oxygen to combust some of the carbon, and then a little bit of it reacts with the chlorine, it's very, very likely that it's Martian. And we're really seeing those compounds from Mars, but formed by chemistry in our cup. So that's not as fun as if you had a whole bunch of compounds that just got released that are complex organics that you might see, but this site didn't give those to us.
So I know that Curiosity has a testbed equivalent rover
Yeah.
At JPL. Does that have instrumentation in it as well? Like, do you practice a SAM run in a testbed here on Earth and
Yeah.
the entire SAM system?
Great question about the test bed. We thought about that originally, and the problem is JPL has a much heavier atmosphere when they run it at Earth atmospheric temperatures, Earth atmospheric pressures, and so we don't. We just have some simple stuff there. But what we have back at Goddard, where I come from, is a full-up SAM test bed in a Mars environment that looks just like the rover, other than it being a big square vacuum chamber. The thermal interface, which is really important, models the cooling loop that comes from the RTG, the radioisotope thermoelectric generator, with the same piping and everything. And then we run that at Mars ambient pressure. We have thermal shrouds on the side that make it look just like the rover temperatures on Mars, which on the bottom, of course, gets very, very cold at night. It's always in the shadow. So we go through this really time-consuming, rigorous process of when we want to do a new experiment on Mars, which is just about every single time now, we think about what we want to do. We write a script, which is a commanding language that looks like BASIC. We review the script. Then we run it over to our test bed at Goddard. We run it. If there are any problems, we fix it and we run it again. Then we review the script again, make any changes that are necessary for Mars. Then take it back to JPL and get it through their system, which is kind of their review that we're not going to do anything that consumes too much power or anything like that. So it's a test bed. We just use it constantly before we do anything on Mars. But it's at Goddard, not at JPL.
And just quickly following up, so I know that there's another sample from the original SAM sample you're going to run again. SAM sample through SAM, right?
We are running it at this very moment.
At this very moment. Are there a limited number of runs you can do with SAM? Because I know there are a certain number of containers. Is there a maximum number of times you can use it, or is there things that can be done?
Yeah, we get that data down tomorrow, so we'll see what we get. We have 59 of these quartz cups, and their volume is about 9 times the volume of sample we're getting now. So in principle, we could drop a new sample on top of the old devolatilized residue, and that wouldn't be quite as squeaky clean as dropping it in a new cup, because you might do some chemistry with the residue, but we certainly could do that. I think, going on 4 months into the mission, and we've used 4 cups now. And so, clean cups should keep us going for a while.
So you can theoretically, you can do hundreds.
That's right,
If
yeah.
you just kind of take into account the previous one.
So originally, when we were all optimistic about how many samples we might do before all the nuts and bolts of the planning started, the scientists all got together. Well, you might want to analyze about 75 samples. So we actually built 74 cups. We now have 6 of them are calibration cups, 9 of them are wet chemistry cups, and 59 of them are these quartz cups of the type of experiment that we did. So what will limit us eventually for chromatography is our helium reservoir. We have 2 helium tanks, and we size those to be twice 75 samples. And so, we should be well past the end of the nominal mission. We should still have helium left. If everything's working, we might go on for years, but we'll see how it goes. Keep our fingers crossed.
Good problem to have.
I'm sorry?
It's a good problem to have.
It's a good problem to have. Yeah, we'll be really glad when we get into our first sample of solid rock, because that's been one of the big mission objectives, drill into a rock and get
Can you
samples.
say when we can expect that?
We're hoping to be by the rock that we're going to drill by mid-December, coming right up. And it would be really nice if we could get a sample in before the end of the year. But again, the test bed that they have at JPL has drills and everything, and any little problem they find, they just look at very, very carefully. So the guy named Pete Tysinger was the old project manager, and then he left once we landed. And he told all the crew at JPL, this is a national asset, don't break anything. And so people are being really careful. They can anybody almost at JPL that's in the tactical link, if they have a question, they're supposed to say, hold the show, wait till tomorrow. Solaro, we call it, not tomorrow. But
How many people are on the SAM team? 'Cause I think we see like the PIs and we see those people,
Yeah.
but I realize now, having been to NASA Ames and seen the Kemen, there's tons of people. How many people work on your
it's not a people. We have about 40 on our science team. Some you may know, Chris McKay and Lori Leshin and others. We have an ops team of about a dozen because they work multiple shifts and they work every day.
Are they at Goddard or are they?
We were at JPL for the first 90 days working on Mars time, which was lots of fun.
Yeah.
And now we're at Goddard, and they kind of work at JPL 8 a.m. to 8 p.m. shift, but it can shift a couple hours earlier or later depending on when the downlinks are. So nominally at Goddard, we're 11 to 11, but then if it shifts later, we're at 1 to 1.
Wow.
But we have French colleagues in Paris, and their operations center is in Toulouse. And so, of course, 8 a.m. is 11 a.m. East Coast and is 5 p.m. to 5 a.m. in Toulouse. So they have the fun job, I guess, of staying up all night for years on end.
Science.
So did you, you're the PI on SAM, did you come up with the concept to put into Curiosity, or were the requirements of Curiosity that it contained gas chromatograph and tunable laser spectrometer and all the other things that SAM has in it? And
Yeah.
then you proposed the actual mechanics of it to fit into it. And then going along with that, how long has it been since you made your first proposal to be involved with Curiosity?
Yeah, it's more of the latter. What NASA tries to do is make everything competitive, try and get the best teams out there, which are both science and engineering. But they try not to be too restrictive. So what they do is they'll get scientists to kind of get mission objectives. The mission objectives for Curiosity were do a lot of different things, but it included measure isotopes and do this kind of broad search for organic compounds. And so our particular response to that was this combination of a GCMS, 2 instruments, with the JPL tunable laser spectrometer, because that really precisely nails some of the isotopes that we couldn't get very well with the mass spectrometer. So all that implementation was our idea, myself working in concert with other people, see if they wanted to join us, try and get the best people on board and that type of thing. So it's more of the latter. And we started, I would say, thinking of, we knew the mission was coming up, so in 2002, we asked NASA for some development money, and we got a little bit, not as much as we needed. And then in 2004, we wrote the proposal, and right around this time of year in December of 2004, we got awarded the instrument. And so it was lots of fun going forward from there because a lot of things like how we would interface with the rover and all that hadn't really been worked out. So we spent a lot of time, would we couple to their thermal system, would we have radiators? And so we reworked our basic instrument configuration many, many times before we really settled in.
I hate to say it, but we have
Sorry,
to move it along here pretty soon. We're going to make it over to the session at noon in Muskogee North.
Yeah.
Any final questions want to throw out real quick, or one more?
Jess, what do you think are the prospects of finding complex organic molecules on Mars? It's kind of a big speculative question, but just want to hear that.
I wouldn't be surprised either way. But, you know, ancient Mars, how long did the water stay around, and how did those environments preserve or not preserve organics? I think it's certainly not impossible. You know, lots of organics are falling into space, aside from the question of life or not, or aside from the question of whether prebiotic chemistry happened. And it's just a matter of, can we find an environment where from billions of years ago those things were preserved? The layers of Mount Sharp are what was our best attempt at finding a good place on Mars to look for those like clays and sulfate layers and so on. You know, we weren't going there to look at this dust pile, but that sure was fun. But yeah, probably months from now or maybe a year from now, we'll be in a good position to say, yeah, we kind of didn't really find organics, but we know we'll find a lot of other things that tie to past environments. So I'm optimistic.
Thank you.
Thanks.
Thank you. Good luck with your tour, guys.
Good luck with yours.